For problem number 5, we are working on a wooden block that collides into, a bullet that collides into a wooden block at rest, and then it launches the wooden block around this ramp. So in the first question, we want the minimum velocity of the bullet, and let me get a, so minimum velocity of the bullet that enables the block to rise to the top of the loop. So this is where we want the block. And since it's the minimum velocity, it's just gonna rise it up to the point where it's at rest. So in this scenario, we are going to take conservation of energy. We've got energy here at the top, which is momentarily stopped because if it's minimum velocity, it's going to have no kinetic energy and it's gonna have all gravitational. And then we have the motion of the bullet in the starting position, but we can't have conservation of energy before the collision because the collision actually loses energy when it's inelastic. So what we want to take is the energy when the bullet has already hit the block and it is at its maximum velocity, it's at a combined velocity moving to the right. So that would be all kinetic energy here at the bottom, and then kinetic energy with the bullet inside of it, gravitational energy with the bullet inside of it at the top. So in this scenario, we're going to take the kinetic energy, which is 1/2. The mass would be the total mass of the bullet and block, and then we don't know this final velocity. It's equal to mgh, which is the total mass again. And then the height would be the height of this circular ramp. And since a radius is r, we want to double that to get the total height. So in this scenario, you can go through the calculation, but we've got velocity squared. I'm going to multiply the 2 over, and I already noticed that the masses cancel out. So I get velocity squared equals 2g times 2r. And then when I take the square root of that, I end up with the 2's. I can pull that out, and I get 2 square root of gr. Now that's not my answer. That's just this velocity right here. What we want is this velocity. Now, as I stated, the kinetic energy is not conserved when we have an inelastic collision, but what we do know when we have an inelastic collision is that momentum is conserved. So I'm going to use P initial is equal to P final. My initial momentum is just the momentum of the bullet because the block is not in motion, and then it's going to collide together to make one mass. And then the final velocity I calculated from up here, which is 2 root gr. And then from there, we can simplify. I get V naught is equal to 4m over m times 2 root gr. And these end up simplifying down to 8 root gr. So that is the velocity of the bullet to get the bullet block to the top of the ramp. For part B, we want the minimum velocity of the bullet that enables the block to complete the loop. So in order for it to complete the loop, we are going to end up having both gravitational and kinetic energy at the top. And we are going to, again, because of conservation of energy, energy is only conserved after the inelastic collision. So I'm going to start with all kinetic energy at the bottom, and then I am going to end up with part gravity and part kinetic at the top. So I'm going to start with this first. One thing I want to emphasize is that we cannot start with kinetic energy of the bullet equal to the combined kinetic energy at the top of the ramp. because of the energy loss through the inelastic collision. So this is going to be a 3-step problem. So, or 2-step problem. So the first step is going to use conservation of energy. I have kinetic energy at the bottom, and it's of the bullet and block. So I'm going to go ahead and add them together and call that 1/2 4mv squared. And I don't know that velocity. I am going to set that equal to 4mgh, which is 2r, and add that to 1/2 4m v, I'm going to call this velocity at the top, squared. Now, what I need is the velocity at the top of the ramp. So to do that, I am going to use my concepts for my force unit. At the top of the ramp, I have gravitational energy pulling down. I also have a surface, so I'm going to call that the normal force, but the problem is we want to find the minimum velocity. The minimum velocity that gets the block around the ramp is going to have 0 normal force. So if you think about a really fast velocity, the faster the velocity, the greater the normal force. It adds to the gravitational force pulling down, and you feel like you are being pushed against the ramp. But if I go at the minimum velocity, then essentially the normal force reduces down to, gets smaller and smaller until it reduces down to 0, and the only gravitational, it's only the gravitational force that creates that centripetal motion. So this is a Newton's second law equation, except it's in circular motion, so we have mv squared over r. And the only force that is acting on us is mg. And so we can solve for this velocity at the top by solving Newton's second law equation. So Vt squared is equal to gr, and I take the square root, and I get square root of gr as my velocity at the top. Okay, now I'm going to solve for the velocity at the bottom. So here I'm going to simplify this down to 2mv squared is equal to 8mgr plus 2m, and I need v top squared, so that's just going to give me gr. And then when I simplify all of this down, I get v squared is equal to 10mgr all over 2m, and this cancels out, this reduces to 5, and when I take the square root, v is equal to 5gr square root. So that's not, again, my final answer. That's just the velocity of the combined block bullet moving to the right. So what I need, again, is conservation of momentum. So I'm going to take my P initial equal to P final. My initial is just the mass of the bullet times the velocity is equal to the kinetic energy of the bullet block system moving to the right. So I get the combined mass, m plus 3m, times this velocity at the bottom of the ramp, square root of 5gr. And then when I reduce everything, I get 4m over m, square root of 5gr, which reduces down to 4 root 5gr. So for part C, we are going to start with our Newton's second law. Again, I have the block at the bottom of the ramp here, and so it's got a force of gravity pulling down and a normal force pulling up. And these forces are not balanced because of the fact that it's moving in circular motion. So my sum of the forces, centripetal forces, is normal force minus gravitational force is equal to mv squared over r. But I have to include both the mass of the bullet and the block. So my normal force is equal to, minus 4 mg is equal to 4m. V squared is the velocity of the block at the bottom of the ramp, and that I calculated up here in my diagram. It is square root of 5 gr, but if I square that, I get 5 gr all over r. And these end up canceling out. If I bring my 4 mg to the other side, I get 20 mg plus 4 mg, and I end up with 24 mg for my normal force.